Okay, welcome everybody. Last week before the Christmas holidays, so give all the energy you have this week and then have some nice relaxing times. The topic of the lecture today is managing raster data in the database or not in the database. That is the question. And I will start with a short poll again, as usual. And I will go to the raster data poll. And I think you should now see the options, two questions as usual. Why store raster data in the database? You can indicate multiple options. One option is you can use the indexing, the clustering. It has good support of multi-user updates. There is no overhead. You can combine it with other data. Support for metadata. Access right management is well arranged, so who's allowed to access and who not, and update, read, write. And the second question, a bit more specific, is that in the Oracle raster solution, is the data and the metadata separate or is it combined? Okay, so far 3 sets of responses have been received. I'll wait until I have at least say 10 responses. So now 7. So 3 to go before I stop the polling. 9 in now. I'll count down. 5, 4, 3, 1. Okay, 10 in and I end the polling and I will share the results. And yeah, the first question is why should you manage raster data in a database? First option, index and clustering. Yeah, that's indeed correct. Multi-user updates. Yeah, it is possible. Supported by the database, but not really needed. So it does not happen quite often that multiple users are updating the same raster. So for this reason, the database is not really needed. No overhead, mean and lean. Also, that is not true. The database has some overhead. And an efficient file solution can, in that sense, never be beaten. But the other options are again benefits. You can combine it with other data types, vector data, alphanumeric data. You can manage the metadata very well. And also the access rights are managed well. So who is allowed to read the raster data, to update. And so only multi-user updates and no overhead is wrong, and the others are correct, the other options. Then the second question, and okay, everybody had the right answer here. Oracle indeed separates the metadata and the raster data in separate tables. Okay, I'll start now with the lecture, but you already seem to know a lot. So let's share my screen. Go to the lecture. So until now we discussed really a lot of vector data, the points, line, polygon stuff. I mentioned some raster data, but I basically forwarded it to this lecture, and also in the lab assignments, worked with vector data and alphanumeric data in the lectures of in the labs of Wilco. And in this lecture, raster data or multidimensional arrays will be discussed. I will first try to give you a motivation why I think it's important to have raster data in the database, though there are some drawbacks. Then I will make an inventory of what should be supported by the database. And then two relational databases are discussed that do support rasters, Oracle and PostGIS, with different solutions. And as last part, we're going to look at the multi-dimensional array database, but there are many similarities with raster data. But this is a specific database designed for this purpose, and it's called GeoDB. And actually, that part of the lecture is based on the master thesis project of Haicheng Liu when he was still a master student. Okay, why would you not store raster data in the database? You could say rasters are often static. So once you take an image, yeah, that image is fixed. You are not going to change that image. They have rather simple values, so just RGB values or intensity values, and there are no references like the primary key, foreign key stuff. So there's not really a need for this advanced, sophisticated multi-user update and transaction mechanism facility supported in the database. Rasters are by nature rather large. If you have a high resolution image of satellites or aerial imagery, they are really large data sets, many gigabytes, even terabytes if it's nationwide. And yeah, the support of raster data is not that well, and you can compare it to vector data, and the conclusion is that raster data is at least 10 years lagging behind in database management support. So it's a bit like in the early days of vector data. The support was limited, not standardized, and the same is true now for raster data. There is some support, it's limited, it is not yet standardized well. But despite this, there are very good reasons to store raster data in the database, and you already indicated a number of them in the first poll. Having also the raster data in the database gives you a uniform shared access to the data via the SQL interface, with managing the rights of the users. You can access this from different clients. Can be a desktop, can be a web-based client, can be a graphic application, can be a terminal application, doesn't matter. And the database can respond to the SQL queries. The database makes sure the storage is reliable, there's integrity, it's secure, there is backup, there's replication if needed. You can configure the database that there are multiple stores. And in general, it's very scalable. So if you have a lot of data or many users, then a database is a right solution. But how does it work in the reality compared to the well-known file formats? Okay, and here it does help that we already have some efficient techniques for spatial access, the indexing and the clustering. And when we have a function in the database, then everybody can use that function, and not only the one using a specific program or a self-developed program. No. All users of the database can reuse that function. The database is also very good in managing the metadata with the rich structure. What was the resolution? What was the camera used to do the observation? What was the date? And so on. And if we store the raster data in the database, we can also do over there the operations. There are all kinds of raster data operations. And the answer may be very small, But if you would need to transfer the data out of the database to an application, that could be a lot of data. But just getting the data of the answer of an operation, that may be a very modest or limited amount of data, so very efficient. So it's always good to do the operations there where you have the data. And I think one of the main reasons to have your data, your raster data in the database is to keep them organized. Files get lost, metadata gets separate from data, and in the database this is all managed very well. Okay, let's have a look at what we expect from a database to provide raster data functionality. And there are indeed a number of options available, like Postgres and PostGIS. There's the raster option. Yeah, it's available, but it's still under development, so every year it gets a bit better. Oracle GeoRaster, it is in production. But both of them are not really an ISO or an OTC standard, and they are different. And then we have other databases tailor-made for this type of data, SciDB, and the support of raster data or even higher dimensional arrays, 3D or 4D arrays, and more detail later. Okay, what do we expect? Okay, we want to store the raster data in a proper data type. We want to be able to do georeferencing or change of reference systems. Multi-resolution. Sometimes you want to have an overview, big area, but maybe a bit coarse. And sometimes you want to zoom into a specific location, a smaller area, but really high resolution. That's called a data pyramid. We would like to have operations, for example, filter operations, or classifications. If we get an image, is it possible to classify which pixels in the image represent the vegetation and which are representing the buildings and the roads? And we would like to have a standard application programming interface, so we can connect from the database also to the raster data to the end applications. There are many data formats available. Every satellite and every camera has its own format. Okay, there is JPEG and TIFF and GeoTIFF. Just a few among the many, at least 1,000 100 raster formats for sure. We need to be able to input and output them, because that is how we get the data. And we want, of course, in the client tools also some support for the raster data, like in QGIS, ArcGIS, or WebGIS systems. Thinking about the storage, because the raster data is so big, we want to be able to optimize and to tune the storage, and that is often meaning thinking about, okay, the whole image could be tiled or organized into blocks of certain size for efficient storage. And also we have to think about compression. And we can sometimes gain a factor of 5, perhaps even 10 compared to the uncompressed image data, raster data. Okay, how fast are the data loading tools? How fast is the indexing? Create an R3 or an OP3. And then, of course, in the end, how fast is the data retrieval? The queries, most important query is the range or rectangle query, but sometimes we just want to get all the pixels of a raster inside the polygon query geometry. Okay, here is a visualization of what I meant with the data pyramid support. And this is about the same area, the same part of the world, but represented at different resolutions or spatial granularity. At the bottom, there is the highest resolution, most detail, and at the top there's the most coarse representation, and in the middle levels you have, say, medium coarse representations. And what you often see with multi-resolution representations in a raster is that at the bottom level, I'll try to depict this here, at the bottom level over here, you see that 4 cells are combined into one cell at the next level, and some kind of computation is used, like average or minimum or maximum, depending on also the content of the raster data. This gives a very natural data pyramid representation. What is also different with raster data is the way, say, the coordinate spaces are organized. In the raster image world, people are talking about the rows. Like this is a row. And the columns are going like this. And also in this direction. So the row is going from left to right. And in the column, the numbering is from top to bottom. And if you compare that to our normal geographic referencing with latitude, longitude, or X and Y, then we have the origin usually in the lower left corner and not in the upper right corner, as it is for the raster. And so that is one of the difference. A second little detail is, okay, about the actual location of the raster cell and the corresponding X and Y coordinate, or row and column index. Is it corresponding to the middle of the cell, or, for example, as depicted here, to the upper left corner? So if you know the coordinates of the upper left corner of this cell, and of course this corresponds to this whole cell over here, and then you can compute the location based on the row number and the column number, in this case both 0, 0, but convert it to a location, and you know the cell size, then you know also the other coordinates of this little area. Most common is the center, and that makes sense, to me at least. Okay, now we have a look at the first system, and that is Oracle. It's called the GeoRaster solution. Basically, in this GeoRaster solution, there are 2 main types of data. The first one is the metadata, and the second one is the actual raster data. And I'll put it like this. There are 2 tables, the metadata table, the raster data table. I will discuss them in detail, but remember that next to the actual raster data table, there is a table which is called blob, a binary large object, and that is where the actual cell values are stored. And good to know that both can be indexed. The metadata can be indexed, like over here, and the raster data itself, or the tiles, can be indexed. Okay, the metadata. Oracle supports different types of rasters. And that's the raster type, which is the first element of the metadata. And there's a kind of code list for the values. Is it a 2D raster or is it a 3D raster? That would mean voxels. How many layers does it have? So D is the dimension, B is the bands, is it one layer or is it multiple layers? Is it a temporal raster? So it's a space-time grid. And yeah, this is an indication how Oracle internally stores it. And this type 01 means external store in a blob. Okay, the raster dataset has an extent. And that can be described as an SGO geometry, for example, the envelope or the bounding box, the minimal bounding box. The raster data itself is stored in another table, and that table name is stored in this attribute. So this was the extent. Every raster object has an identifier, and there is a metadata record, which is one attribute, but that can encode all metadata things that you would like to store of a raster in an XML encoding. And that is for sensor type, original resolution, who's the person that took the image, camera, date, all these kind of things are part of the metadata, the additional metadata. Okay, this is the main table for the real data. It refers again back to the same ID. And Oracle has standard support for the pyramid levels. So if you are then a raster object, you have to know on which level in the pyramid you're living, at the top, in the middle, or at the bottom. Is it 1, 2, 3, 4, etc. Then all pixels or raster cells are organized in blocks, and they are basically three-dimensional, row and column, two-dimensional spatial, and in thematic you have the bands. It could be RGB or infrared, or depending on the sensor type. So row, column, and bands, and that is a kind of organization, but it is the block. So that is so if this is all your cells, and I'll like draw them quickly, and you will understand. All the pixel values, and this is a lot of detail. And then the blocks would be units of bigger size. That could be like this, so one level higher, or a number of levels. And so a block is just a collection of pixels from a certain row to a certain row, and from a certain column to a certain column. So this is then one block. This is a mini example, and in reality it can be 100 by 100 or 50 by 50. And I just depicted the row and the column dimensions, and the same is true for the band dimension or thematic dimension. And every block has an extent, and a minimal bounding rectangle of the block, again stored in the Oracle type geometry. And then we have the blob, and the blob is a pointer to a binary large object, a kind of storage in Oracle, where then all the pixel values are stored. Okay. Initially, when you load a raster image, it does not have a data pyramid, and this little pale SQL script shows how you can create a data pyramid on top of this lowest resolution by calling the function generate pyramid. And the raster data is stored in this table indicated with this variable. So this is passed over here, and we ask for 5 levels in the pyramid. And for the interpolation, the technique is bilinear. it's a stable and mature implementation. There's quite a lot of functionality for storing, retrieving, in and output, you could say. It has limited functions, but a nice set of functions that has been made available is the map algebra. And I hope you remember this from the Introduction to JS course in Q1. I'll do a quick refresher later on. Next slide. The Oracle raster data is not that well integrated with vector data. And it does also not really have true three-dimensional support, either in space or 3D as the time dimension. And it is basically the row and the column and the band. That's hard-coded. Okay, map algebra. It's a cell-by-cell combination of manipulation and computation of raster data layers. And this is raster A. So this raster A is the name of the raster. And here is the raster algebra. So this expression say, okay, C1, raster C1 becomes raster A plus 10, and that means so every individual value, 10 is added. And then the output is raster C1. Here is another map algebra expression. C2 is adding raster A plus B. This is raster A, and this is raster B. And at cell level, I do an addition. So 5 and 4, that gives you the 9 over here. And that is done for all values. And C3 is another example, a bit more tricky computation. A minus B divided by A plus 10. That gives you C3. And there are a number of different type of operations there. This was the local operation. If you want to go, remember more, go back to Q1 or check this textbook and look at this section. Okay, this was some sample data, an image of Rotterdam, high resolution image. 12 GeoTIFF images with 24-bit RGB, 600 million pixels in total, and the original data size was little less than 2 gigabytes. It's a small area. It's not the whole Netherlands. It's just a part of Rotterdam. Storing these 1.8 megabyte, 1.8 gigabytes in GeoRaster in the database resulted in a 2.0 megabyte storage. And so some increase. And this is what I meant in the beginning with some overhead. However, you can use the compression option in Oracle on the GeoRaster, and then the size is about halved. So it is reasonable. It's not impressive for compression, but it's reasonable. And when you then add 5 layers, so in addition to the bottom layer, add 4 layers on top of it, then the total size is 1.5 gigabyte, which is still smaller than the original TIFF files. You can do querying, and in the querying, there is basically a 2-step approach. First, you have to figure out which styles do I need. And then if you want to refine, for example, with a polygon or a rectangle, make sure that from the tiles you need, you only take those parts and clip away the others. And okay, that is supported by Oracle, but you have to kind of do that yourself. And that means that the result of a query or the efficiency of a query may depend on your decision how big the tiles are. And so here we had 3 different settings for the tile size. small, let's say, so that here small, and here medium tiles, and over here large tiles. Here we have to get many tiles, and yeah, relatively efficient. Here we get fewer tiles, but yeah, we have a lot of data which we don't need. And here it's we only get one tile, but we really get a lot of additional data. So you could say smaller tiles may be good for efficiency of queries because they can be more precise in the initial phase. So in the second phase, when the exact overlap is done, in this case with the circle geometry, the answer is the same. But in the initial phase, a smaller tile results in less false positives. This is a query geometry. And here you see the pale SQL code, where this two-step procedure is illustrated. Okay, it's time for a short break. Let's pause for 5 minutes. It's now 14:17, so see you back at 14:23. In the meantime, I will have a look at the chat box if there are any queries. So see you back at 14:23, and I will go to the chat now. Okay, I don't see any queries, so that's good. See you back in 5 minutes. Okay, welcome back. Second part, and now we'll discuss the Postgres raster functionality. And as you see, there is a new poll open about storing raster data in Postgres. First question is, okay, what is the benefit of a pipe between two processes? And yeah, the first response is, okay, no intermediate file storage. Second benefit is it allows parallel processing. Third option is, okay, there is no real benefit. And the last option says, okay, only benefits for working with Postgres and nothing else. Second question, yeah, we just saw the raster pyramid support in Oracle. Next, we're going to look at Postgres, but here is the question. Postgres has good support for a data pyramid. True or false? First question, yes, it has standard support, this similar to Oracle. No, it's not possible at all. And the third option is not really supported, but you can load multi-resolution images yourself. Do-it-yourself pyramid creation. Okay, I'm counting down. There are now 8 responses in. And then I will end. 5, 4, 3, 2, 1. Okay, end of poll. And here are the results. And I must say you already have prepared quite well. The benefit of a pipe in combining multiple processes is you don't need to store intermediate results. And the output of one process can be directly the input of the next process. That helps. You don't have to write, you don't have to read the file. No I/O to disk. Process to process communication is more efficient than writing to files. And it also makes parallel processing possible because one process can run and produce outputs, and in parallel, the second process can already start reading input and doing also work in parallel. So no real benefit is not true, and it only works for Postgres. That is also not true. It is really a generic solution. Second question, Postgres has good raster support for pyramid data. Yes, it has really standard support. Okay, this is not true, as you will see in a moment. It's also not true that it is not possible at all. It is true, but you kind of have to do it yourself, creating and loading the multi-resolutions. Okay, I'll now share my screen and continue with the slides. And the last 2 parts, raster data in Postgres. As you all know, Postgres is the spatial, PostGIS is the spatial extension of the PostgreSQL database. PostGIS uses a number of libraries, the Proje4 library for the coordinate transformation, the GEOS geometry engine open source for topological relationship between geometries. Remember Egenhofer, Clementini kind of operations. And it also uses the GDAL library, the geospatial data abstraction library, where a lot of raster support is, input, output, but also some operations. And PostGIS is building on this. What they state themselves in the documentation is that they have a kind of minimalistic yet complete raster data structure, single type, single table relational schema, comparable to the vector data types, and very different. What they state in their documentation that they are very different to Oracle with the SGO raster and the SGO GeoRaster for data and metadata. And they continue, much simpler. And before the Postgres raster, there was also the PG raster solution for Postgres SQL. And so it's claimed to be simpler than both their old solution in Postgres and the solution in Oracle, and giving support for one data type. With no difference between data and metadata, een raster en een tijl. Een tijl is een raster en een raster is een tijl. And the metadata is in the same row, in the same object. It does also not support multiple dimensions, like the X, Y, and the Z is a 3D grid, or the X, Y, Z time. But the same as Oracle, it does support bands, so RGB. And it does not support standard pyramids, but you can, say, create multi-resolution raster coverages and store them as different layers. It is very similar to vector data. So in one table you have one coverage, not per se rectangular, and one row is one object, and an object is basically a tile, part of a raster. There's one data type, just raster. So for vector you have point, line, polygon, but for raster there's only one type, raster. It is self-contained, have both metadata and data, but does not contain references to elsewhere, no pointers. The aim is to have good integration between raster and vector data, so there are really a lot of operations that you can apply, the same operations that you can apply both to the raster and the vector data. And there's a good conversion from vector to raster data. So if you have lines or polygons, you can create the raster versions out of them. There is an option to store the raster data in the database, and there are read-write operations, and there are conversion operations from vector to raster. And there's also the option that you keep the file and that you have a kind of wrapper around that file that makes it look like a table in the database with all the functionality and all the possibilities to do a join with another table and to do queries. And so that's the in-DB and the out-DB storage. And so the biggest goal was to develop a simple solution that worked seamlessly between raster and vector data. So they developed a lot of functions, raster functions of the existing geometry functions that were available on the vector data, like compute area or intersect. They have conversion functions. The easy one is vector to raster. Per se not so easy, but it's rather easy. Raster to vector is more hard. If you have a raster with a number of pixels black that should represent a polyline, that is not a trivial operation to get that polyline in the white background. And usually the background is not that clear white and the foreground is not that clear black. Maybe you are looking for a car in an aerial photo. You want to have the contour and the outline of that car, the polygon. But they try to give support for that. So all the vector type of functions work also with rasters, and all the raster functions, they also make it work for vectors. That is really a nice approach. It is a single type, single table solution. And that allows you to do all kinds of different things. You can have even overlapping images you store. So all these red blobs over here are records that you store in the raster table. They are tiles, big tiles in the raster table, 4 big tiles, 4 images. Actually, they're not really tiles, but you could say a tile is an image. It is just one tile, one image, one tile. Here, the different images are tiles, a bit irregular. Look, the tile size here, the boundary is different from in the interior. So 36 tiles in total. Here we have more regular tiles, but not a complete coverage of a rectangle. In this area there are no tiles, and also over here, but all tiles are same size. 36 tiles. Here we have the most normal situation. Rectangle area completely covered with non-overlapping tiles, 54 in this case. What you can also do is create 2 tables. In one table you store a raster coverage, and in another table you store another raster coverage. That could be an image of another date, or this could be an image, and the other one could be, say, classified pixels like vegetation, water, and other objects. So that's possible. Yeah, because it's a different type of information or a different date, you store it in a different table. But if you want, you could also store this overlapping. It gets messy, like over here, but it's possible and allowed. And you can also store a kind of raster collection of objects. So this is a line, this is a polygon, this is a small line, polygon, a point, this is a line, rasterized, polygon, rasterized. So there are 9 objects, say in vector terms, point lines and polygons, but converted to rasters and stored in one raster table. So this is a table with 9 records, all of the same type, of the raster type, in this raster coverage table. It's not really a coverage in this case, but it are objects. Okay, this raster type we did not yet discuss, but as you can see here, it is not super simple. There are really a lot of attributes, but they are not that hard to understand. For example, the number of bands, the width and the height. These are primary organization indicators of the rows, the columns, and the bands. You can give an indication of the pixel size, indication of the lower left coordinate. You can specify a rotation angle, spatial reference system. You can have separate information on the various bands. So yeah, you really need this information to understand your raster data. Okay, claimed many times, but the rich functionality in PostGIS raster. And it's a bit abstract if you just say there are a lot of functions. So here is a list of functions in a number of different categories. Functions to set or to get raster properties, like set the metadata description, set the height and the width, or get the height and the width. Set or get the spatial reference system, query the lower left X, or the rotation metadata, and so on. This is about the raster level. Then you can do the same with the different bands. So ask how many bands there are, or set the number of bands to 3 bands or to 4 bands. Okay, some more real data functions are getting and setting pixel values. So you can get either an individual pixel value, a cell value, or you can get a whole set of cells, usually a subrectangle of the whole domain. You can even change it, change the value, which is strange. So changing an individual value is a rather uncommon operation, but it is possible. There are functions to create new raster objects and to add bands to an existing raster object. More functions to do spatial analysis in the sin of intersect or intersection computation. So intersect gives a Boolean true or false, and intersection gives you the intersecting geometry. Converting to a polygon, or compute the convex hull of a set of raster objects. For example, you can imagine that you can compute a convex hull over here. Oh, this is not a nice thing. There's a convex hull looking like this. Okay, it's a bit like a rectangle. It does not need to be a rectangle, just a convex shape. And really also some really nice raster operations like resample, rescale, reclassify, clip from the raster, combine rasters, and finally a lot of output functions to convert to different formats. Output is JPEG, output is PNG, output is TIFF, output is GDAL, raster, and so on. There's a rich library of tools available. Application programming interfaces to Java, PHP, Python, C#. Tools to load data. They are based on the GDAL library, these load tools, the input tools. And okay, it's nice to have data in the database, be able to do operations with it, but also nice to see it in the front ends, like QDS or FMA, and also GDAL has its own viewer, and you can access, store, or update, or query data in the database and visualize them with these tools. Okay, I realize it's a bit abstract. It's all about eating the pudding, so doing the queries in database terminology. And so Postgres raster is a specific package in the database, and you can check if you have your package being enabled by this query, and also which version you have. You can create a raster table, create a table dummy raster with two attributes, an identifier and the raster object, so either the complete image if you don't want to tile, or one of the tiles. And you can start inserting or populating the raster, insert into the dummy raster table both identifier and the raster values. So ID1, here the raster values converted, casted to a raster, and the same over here. And then you can start asking queries, select the width of the raster I inserted here, the first and second row, the height, the number of bands that these rasters have. You can have a kind of binary or text encoding of the raster, a bit similar to the well-known text for the vector types from the raster table. A little bit about loading, because yeah, raster data, you don't usually do it with a lot of insert statements. The source imagery is often stored in files like TIFF or JPEG. And what you always best do is kind of analyze the file you have. And the file I have here is called testimage.tiff. And now I want to know the metadata of this file. And I use a tool, a program, GeoDBMs exe. And that gives me the area, the size, the coordinate reference system of this TIFF image. I don't see the image yet, but I have the meta information. And it's not stored in the database yet, so this is completely independent of the database, and no database here. Okay, once I have understood the content of the file, say, yeah, this is what I want. There is actually a two-step procedure to load the raster data into PostGIS. An important program is raster to PG SQL. That is a bit, the conversion, the hard work in the conversion, or easy work, depending on what you want. You can specify options. And it's also it's like a command line over here. So here is the function. There are a whole set of options: min s, min t, min y, min I, and then I have here a little bit different like this. I have my input file, and this is the table name where I want to store my raster data. Okay, the options, min s, obvious. Well, obvious if you know. This is a spatial identifier, a spatial reference system. This is RD in the Netherlands. Tile size, the width and the height of a tile. And so I want 500 by 500 tiles. The image may be 5 by 7 megapixels, but okay, to store the image, I want to put it in chunks of 500 by 500. And the min y is, okay, do not use the insert statement, but use the copy statement. And the last one, the min I, means create a spatial index. Okay, this is the first step. The output of this first step is stored over here. And this is an SQL file. It's stored in a temporary file. And you can access the content of this file, have a look at it, and you see all kinds of SQL statements that load, that give comments to load the data. And the actual data loading is then done here in the second step with starting the program PSQL, and then as input the same file. And so this is the same file. And you store it in the Postgres database, in the test database. So two steps. The first one only creates a series of commands, SQL commands, and the second one is then executing the commands, and that causes the actual data load. Okay, then the piping topic. So instead of storing the intermediate result in a file, that is Rust SQL file, Rust to SQL file, this file. And especially when in this file there is a lot of data, for example, when the data is really stored in the file, in the intermediate file, that takes a lot of time. Writing to a file means also writing to disk, not efficient. So to solve this, you can combine the two steps into one step by an operating system functionality called piping, and that is supported in many modern operating systems. I would say all. It originated from Unix or Linux, but is also supported now in the Windows and iOS. And it's indicated with a bar symbol. So this symbol, the vertical bar, connects the two parts. So here you see the bar. In red, I have my first command that is creating the SQL statements to load the image data, and the second part then is executing these statements in the Postgres database. And the benefit of a pipe is that it is more efficient than storing it intermediate also in the file. And because you have this now written in this way, the second process can already start when it receives input with executing. And yeah, some types of processing is very suitable for this kind of piping, and then you can benefit of say multi-core processing, or and most modern computers have now multiple cores, so and then the whole task is finished quicker than step by step, sequentially. Okay, one limitation, or there are some limitations. One of the bigger limitations is that it is basically also 2D, same as Oracle. Okay, with bands, and with bands you can do tricks. But okay, it are really tricks. And it does also not support, say, fancy rasters. We'll give you one. Okay, one obvious thing is that the tiling is really do it yourself. And you make the tiles, you index them, and if you want to have multi-resolution or data pyramid, you also have to do it yourself. So it's simple, but with this simple functionality, you have to build your own more advanced functionality. And what is not supported very well is grids like the one that is depicted here at the bottom right side, over here, which is used quite often in modeling in rivers in hydrology. And there are also other types of images where you do not have really a nice regular grid, but a grid with based on oblique imagery and with some perspective in the image. These are also not supported in a standard way. Okay, let's have a 5-minute break again, and then we'll continue with the last part of the lecture today, that is having a look at a specific multi-dimensional array database called GeoDB. I will check now the chat. Okay, still no questions. For your information, the lab on Wednesday will be about PostGIS raster. You will load then some raster images yourself in the database, do some queries. Compared to the earlier exercises, it's a little bit harder. I'm not sure if you have already tried it, but you will notice it's a bit harder. But it should still be doable Wednesday afternoon. I also do hope that the building is still open and that we are allowed to enter the building, because the Dutch government is thinking about all kinds of additional restrictions to further limit the spread of the coronavirus. But as far as I now know, our building is still open on Wednesday, and you can do the lab under the supervision of Marianne. Okay, 5-minute break, See you at 15:55. If there are no questions now, and again, for questions, you can use either the chat or just open your microphone and interrupt me. Okay, let's continue with the last part of today's lecture about SciDB. And SciDB was investigated by Haicheng Liu, and Haicheng Liu was the person that is also checking your lab assignments. I'm not sure if you noticed it. He's a PhD student today. And his PhD topic is about point clouds, but that is not the topic of the lecture today. That will be after the Christmas break. Haicheng Liu was doing his master thesis topic at a company called Hydrologic, which is also Delft-based. And they do all kinds of modeling and predictions of rainfall all over the world, not only in the Netherlands. And so they are heavy users of multi-dimensional arrays. And in that world, the NetCDF standard, which means the network common data format, is kind of the default. A bit like the JPEG and the GeoTIFF are default for normal two-dimensional rasters. And for multi-dimensional rasters, this is the standard. And it is developed by a consortium of cooperating universities in atmospheric research. And it is now also standardized by OGC. There are multiple versions of the standard. So the idea was to compare the efficiency of storing the same data in NetCDF and in a multi-dimensional array database. So Postgres and Oracle cannot be used because they can only store two-dimensional and data and not 3D or 4D or even higher. So, okay, what is a multi-dimensional array? It's a bit the same what we already discussed is the grid. You have rows and columns, then in multiple dimensions. And quite often, 2 dimensions are spatial, latitude, longitude, and the 3rd dimension is time, how things change over time. So here the time granularity is 1 day, and the spatial granularity here is 1 minute in the degrees. So this is a multidimensional array, also called a data cube. And we can take out 1 layer, and that is 1 moment in time, 1 day, for example. And then we have the whole image of the spatial domain. But quite often, what these people want to do, that are studying rainfall hydrology, is look at a specific location. So here we have again our data cube, latitude, longitude, and time. And now we want to look at, okay, what is happening on 1 location, for example, Delft. So we take 1 cell value, latitude, longitude, but all times, from the beginning of the year to the end of the year. And okay, now we are going into the physical organization of this data. And so every raster is stored like this. So this is at the bottom, grid 1, this the bottom. And we have the top. Here you see the cell numbers with the values, or better said, the values. And it's repeated. And if this 3D data cube is stored in the computer memory, it will actually become a 1-dimensional kind of mapping. And if you now look at this column that we want in these different grids, 1, 2, 3, 4, from different times, they are really stored far apart. And when we start reading, that takes a lot of time. And that was the reason why the company Hydrologic asked us, okay, do you have a master student that wants to investigate this topic? Can it not be better? Okay, let's go back to the multiple dimensions. What dimensions do we have? Okay, 2D, space and time. That will be 3D together. Maybe also scale has a dimension. See the lecture Friday. Or 3D space and time. That would become a 4D hypercube. Very difficult to draw. Or what the people in hydrology often do is they have multiple runs of for example, the whole world every 5 minutes for 5 days ahead or 6 days ahead. And they do it many times, either with random variations in the model or with different settings of the parameters. And that gives many different runs. So as a result, that gives a kind of 4D hypercube. 2D space, 1D time, and many different runs, and many different trials. And then by looking at the spread of the different runs in values, you can be more or less certain about the prediction. What Haicheng did was compared NetCDF, the original format, and SciDB. But in the meantime, also CDF4, an improved version of the CDF format, became available. And as I will show you later, that it was very relevant. He had specific data sets, 2D, 3D, and 5D of different sizes. He interviewed users in the company and external users of the company what they wanted, the typical type of request of queries, time series, raster subsets, for example, select one country, explore the different storage options, the tiles or the chunks, or compression on and off. Then he set up a kind of benchmark environment. He executed the benchmark and yeah, he got results. First looked, of course, are the answers the same of different alternative storage mechanisms, but basically doing the same query. And that is a check. And then looking, okay, what does use more storage space? What is responding more quickly for what type of query? The two main data sets were MPE, the multi-sensor precipitation estimate, or simply stated, the rainfall rate. It's a global data set derived from satellite data. It is 2D plus time. And another data set was the GEFS, the Global Ensemble Forecasting System. And that was actually 5D, longitude, latitude forecast, then the set of parameters to do predictions, and then different runs. And for every parameter setting, I do at least, say, 20 different runs with different outcomes. And for different parameter setting, at different ensembles, I do again 20 different runs. And so that gives a 5D data cube. So there are many things that have to be considered. The data set size, the chunks, how big do you make them, the tiles, 100 by 100, 50 by 50, 500 by 500. If at least you can influence it in the storage format, because that was one of the problems that was not possible in NetCDF. Compression was possible. And can you somehow influence the order of dimensions? You could say in this storage over here, the X and the Y are kind of combined, but then the time is separate. So time is the most important in ordering. So this is time 1, time 2, time 3. And in between, I have all the locations. It's also a bit related to what we discussed last week with the space filling curve. So somehow we want to have a multi-dimensional domain mapped to the linear memory of a computer. And this ordering of dimensions or the priorities can have different effect on the queries. Before starting full scale with benchmarking, he did first a small subset to explore most plausible options that worked well, and then tested them further. And this is a bit what I wanted to state also with how do you organize your, for example, 3D data. I have here a data cube with X and Y and time. And the X and the Y have a width of 16 by 16, width and height of 16 by 16. And the same for the time. So it's a cube 16 by 16 by 16. And the first way to store it was, as we explained in the beginning, we do a time slice of 16 by 16 in 16x, 16y, and 1 in time. And so this is the total volume. But you can have the same volume, space-time volume, if you would store a little block like this, 4 by 4 by 16. And so if you count the actual number of cells, this is exactly the same number. Or you could, so here you give, say, the time, you group by time. You could say time grouping, and here you group by location. Everything in this cell is stored in the same block. Doesn't matter if it was early or late in time, they're all stored in the same block. Okay, within the block you also have an ordering, but the block is the main ordering. This is a kind of hybrid, an 8 by 8 by 4, again having the same volume, space-time volume as the others, but it really groups a bit of space, it groups a bit of time, not as extreme as the time slice, or not an extreme as the time needle. Okay, this is able to draw in 3D because, yeah, that's possible. I cannot draw 4D or 5D. But you have the same challenge, how to store your data in which order. And that has a big effect on the performance. The two data sets, a bit visualized. The first is the rainfall 3D, latitude, longitude, and time. And here is some rainfall over here. It's the whole globe. And the same for the GEFS database, 5D. And because here you see the 3D data cube again with latitude, longitude, and a forecast in time. So today, tomorrow, day after tomorrow, 3 days from now, and so on. But you make this data cube for every combination over here. And over here we have the ensemble or parameter setting, how to do the simulation. We have 3 combinations of examples, and then we do 3 runs, or 5 runs, or 20 runs. And so for every cell over here, you have a complete 3D cell here. So in total, it's a 5D data cube, hypercube. Here we see one query. And you see different organizations, different cell sizes, or chunk sizes, or tile sizes. That is in this table here. Comparing the classic NetCDF, or NetCDF4, or the SciDB. And so the organization in cell or chunk size, so this is both, for example, NetCDF4, but with different chunk size, that has a huge effect. Here you see the SciDB values, the database values. And yeah, what can we learn from these responses? Again, these are the typical queries. A time series, so we look on one location and we want to have all times. And again, here another table with the different chunk sizes of this 5-dimensional hypercube, different options. Again, the classic of 46-bit NetCDF4 with different variations and SciDB, and the response times. To conclude, the NetCDF, the classic one, did not perform well in these time series queries. That was the reason that Hydrologic, the company, wanted to investigate this. With SciDB, this could be solved into very decent performance, but of course it had the overhead of a database, so some slight overhead. In the meantime, a new version of NetCDF has also become available, and that, why did SciDB work better. It worked better because it had a chunking option. So you could subdivide the whole multidimensional array into smaller parts. And when you are then querying, just query a part. And the part you could specify the sizes in the different dimensions, the tile size. And that makes the difference between the original NetCDF. However, the new version of NetCDF, NetCDF 4, also supported this functionality of tiling in the file format. And yeah, by also supporting this mechanism, it was also able to get a very good performance. And actually, it outperformed the database because it had no overhead. Of course, NetCDF is really specific, so you have to use the NetCDF library to be able to use, to read, or to query, or to update NetCDF data. You cannot combine it with other data, so all the drawbacks of a non-database solution. But if you only have this data, you don't want to combine it with something else, it is rather efficient. And if you are a single user and you don't want to share it with other users, then you have a very efficient solution. Okay, thanks for your attention. Let me see if there are any questions. No, it is not the case. So I will wait a few more minutes, 1 or 2 minutes, to see if you have questions about this raster database, the different options, from Oracle to Postgres to SciDB and to file formats. I don't see any questions arriving. So let's hope that the measures that are taken this evening by the Dutch government will not affect our lab Wednesday, that we can still have it in the normal way. So I wish you then good luck with the lab. Again, remember, the lab will be supported by Marianne de Vries. And if you have questions before or after the lab, send her an email or discuss it on Blackboard in the discussion page, because she is really much more involved in the labs than I'm at the moment. Okay, thanks for your attention, and see you then for sure Friday, and maybe I walk by on Wednesday. I'm not really sure. Bye-bye.